Today's battlefield is a complex mixture of air power and land power. New technology has resulted in faster, deadlier weapon systems and the use of depleted uranium munitions and armor. Although technology has altered the face of battle, the individual soldier's competence and equipment effectiveness still determine mission success. Depleted uranium is a very dense, inexpensive, easy-to-shape metal, which provides excellent protection against conventional munitions. The same qualities that make depleted uranium excellent defensive armor turn lethal when used as offensive munitions. During Operation Desert Storm, tanks and attack aircraft fired depleted uranium kinetic energy penetrators, which easily destroyed Iraqi armor. Other nations recognized the value of depleted uranium and are developing or already have depleted uranium munitions. In the future, combat engagements, accidents, or equipment malfunctions may result in contaminated equipment. Depleted uranium contamination will not stop the mission unless the vehicle is destroyed or inoperable. On the battlefield, maintenance operations are evaluated in terms of MET-T, mission, enemy, troops, terrain and weather, and time available. As unit maintenance specialists, you must know when and how to manage depleted uranium contaminated equipment. As chemical and medical specialists, you must advise commanders how to control contamination. The objective of this video is to describe contaminated and damaged equipment management. Management consists of 6 phases incorporating 10 procedures. The 6 phases are: 1. Imminent threat or combat. 2. Recovery. 3. Evacuation. 4. Retrograde. 5. Reclamation. 6. Repair. Phase 1. Imminent threat or combat. During this phase, damaged equipment is identified and evaluated. Equipment that can be repaired quickly is repaired and returned to the battle. Phase 2. Recovery. During this phase, damaged and contaminated equipment is covered to prevent spread of contamination and moved to a unit maintenance collection point for damage assessment and repair. Phase 3. Evacuation. During this phase, damaged equipment is moved to the division maintenance facility. They will perform a detailed damage assessment and repair the equipment if possible. Phase 4. Retrograde. In this phase, damaged equipment that has not been repaired is moved to the Corps or echelon above Corps maintenance facility. An Army Contaminated Material Retrograde team will identify disposition alternatives for contaminated equipment if it cannot be repaired. Phase 5. Reclamation. In this phase, damaged and contaminated equipment is decontaminated at an Industrial Operations Command designated facility prior to depot level repair. Phase 6. Repair. During this phase, damaged equipment is restored and reissued to military units. The 10 procedures include: 1. Notify your unit chemical and medical personnel that you suspect depleted uranium or low-level radioactive contamination. Identify the type of equipment and the location. Request assistance if needed. 2. Put on your protective mask and clothing to avoid personal contamination. 3. Perform a visual inspection following prescribed procedures to identify any unexploded ordnance. This ordnance may or may not retain its normal shape and may explode without warning. Only explosive-trained personnel should handle damaged ordnance. 4. Isolate suspected contaminated equipment away from bivouac areas, medical treatment facilities, and any other personnel concentrations. 5. Complete a radiological survey. Use the ANVDR2 with a standard probe or the ANPDR77 radiac meter with the beta flat pancake probe to identify beta and gamma contamination. Use the ANPDR-77 with an alpha probe to identify alpha contamination. Place the white atom sign on contaminated equipment. Mark the type, dose rate, and time of measurement on the sign with a grease pencil. 6. Separate contaminated equipment from uncontaminated equipment. Place contaminated equipment in a marked location and return uncontaminated equipment to the unit. 7. Complete operational decontamination in accordance with doctrine. Radioactive decontamination methods include brushing, vacuuming, and washing. Small pieces of equipment that cannot be repaired nor decontaminated are packaged, marked, and turned in to your supply section for disposal. 8. Repair equipment using procedures described in Joint Service Manual, Battlefield Damage Assessment and Repair. These procedures include covering over fixed contamination or patching holes with paint, cardboard, tape, or any available material. Unrepairable equipment is marked, secured, and left for specially trained teams or destroyed in place. Notify higher headquarters of the location and equipment type if the commander decides to destroy equipment in place. 9. Based on MET-T and commander's guidance, decide whether to use damaged and/or contaminated equipment to complete the mission. 10. Prepare and submit an NBC-4 report identifying the location, type, and level of contamination of damaged, destroyed, or repaired equipment. To summarize, there are 6 phases. 1. Imminent threat or combat. 2. Recovery. 3. Evacuation. 4. Retrograde. 5. Reclamation. 6. Repair. And 10 procedures involved in contaminated equipment management. 1. Notify unit chemical and medical personnel. 2. Put on protective mask and clothing. 3. Perform visual inspection. 4. Isolate equipment. 5. Complete radiological survey. 6. Separate contaminated from uncontaminated equipment. 7. Complete operational decontamination. 8. Repair equipment. 9. Decide whether or not to use damaged and/or contaminated equipment. 10. Prepare reports. Remember, unless the vehicle is destroyed or otherwise inoperable, contamination will not interfere with mission completion. 3 additional videos are available through your Training Support Center, which discuss management operations. 1. Depleted uranium hazard awareness. Pin 710493, TVT 3-92. 2. Battlefield damage assessment and repair. Pin 701358DA, TVT 9-294. 3. The UXO, unexploded ordnance hazard. TVT 9-266, pin 709919. If you have specific questions concerning U.S. Army contaminated material recovery team deployment or management of contaminated material, contact Commanding General, AMCCOM. Attention, Chief Radioactive Waste Disposal Office, Rock Island, Illinois, 61299-6000, DSN 793-1767, or commercial 309-782-1767. If you have questions concerning radiological, chemical, or biological contamination identification and decontamination, contact Commanding General, U.S. Army Chemical School. Attention, Director, Edwin R. Bradley Radiological Laboratories, Fort McClellan, Alabama, DSN 865-4489, commercial 205-848-4489. If you have questions concerning battle damage assessment, repair, and recovery, or BDAR procedures, contact Commanding General, U.S. Army Ordnance Center and School. Attention, Chief of Recovery Division, BDAR, Aberdeen Proving Grounds, Maryland, 21005-5201, DSN 298-2765, or commercial 410-278-2765. If you have any questions concerning unexploded ordnance, contact your local explosive ordnance disposal detachment. Battlefields and fighting are by nature hazardous to your health. Some hazards are easy to identify and well understood. Soldiers recognize the serious hazards presented by incoming artillery shells and bullets and take appropriate actions. However, some lesser hazards from new technological applications are not so well known and recognized. One of these newer applications is the use of depleted uranium in munitions and equipment armor. There are 4 general situations during which depleted uranium may present hazards to soldiers. 1, if the equipment is damaged or destroyed in combat or in an accident. 2, if the equipment has a serious malfunction. 3, if the equipment is misused and or precautions are not taken. Or 4, if you encounter captured or disabled enemy or even some allied equipment containing radioactive material. We need a basic understanding of depleted uranium hazards. What is depleted uranium? How and where is depleted uranium used? What are the potential hazards of depleted uranium? What are appropriate precautions and preventive measures to follow? Depleted uranium is obtained from uranium ore, which is found throughout the world. In the United States, this ore is mined in New Mexico, Colorado, Wyoming, Utah, and Arizona. Uranium ore contains 3 isotopes. By weight, 99.28%, which is uranium-238, 0.71%, which is uranium-235, and 0.0058%, which is uranium-234. Of these 3 isotopes, uranium-235 and uranium-234 are used for nuclear fuel and weapons. Uranium-238 becomes depleted uranium. To separate uranium-238 from the uranium-235 and uranium-234, the ore is run through an enrichment process. The material left is almost totally uranium-238 and a very tiny amount of uranium-235. It is then called depleted uranium because the natural radioactivity is substantially reduced. Depleted uranium is cheap, plentiful, and easy to machine into various products. Depleted uranium has 2 important physical properties. 1, it is pyrophoric. This means that depleted uranium can ignite upon impact with armor or other hard materials, making it an ideal kinetic energy penetrator. 2, depleted uranium is about 1.6 times as heavy as lead. This high density means depleted uranium is an excellent armor plating because very few materials can penetrate it. Depleted uranium is used as armor in the Abrams M1 series tanks and as 105 millimeter and 120 millimeter kinetic energy penetrators for M60 and M1 tanks. Depleted uranium is used in 25 millimeter rounds for Bradleys and 20 millimeter and 30 millimeter rounds for aircraft. A kinetic energy penetrator is a non-explosive round made of a high-density material formed into small diameter rods of various lengths. They are used to destroy armor and other hardened targets. Other uses for depleted uranium include ballast in missiles, as counterweights in aircraft, and as radiation shielding. The 2 main depleted uranium health concerns are 1, heavy metal toxicity. 2, radioactivity. The first concern, heavy metal toxicity, may occur if depleted uranium enters the body through open wounds, inhalation, or ingestion. During depleted uranium impact or fires, shrapnel and depleted uranium oxide are formed. Depleted uranium shrapnel includes any materials contaminated with depleted uranium. Depleted uranium oxide is a very heavy, dull black dust, ranging in size from cigarette ash to small marbles. Because depleted uranium dust is much heavier than normal dust, it is usually deposited on the surface of the vehicle or within 50 meters downwind of the fire that generated it. Depleted uranium dust or smoke may be inhaled if respiratory protection is not worn. It may also be picked up and ingested if gloves are not worn and the dust is not washed off before eating, drinking, or using the latrine. Depending on how much depleted uranium is inhaled, swallowed, or gets under the skin, heavy metal poisoning may occur, which can cause damage to internal organs and tissues. A possible long-term hazard from depleted uranium dust is contamination of the ground and water supply. The second concern, radioactivity, results from the spontaneous emission of alpha and beta particles, or gamma rays, from the atom. Radioactivity emitted by depleted uranium can be detected with already fielded radiac equipment, like the PDR-27 or the ANVDR-2. Health effects of ionizing radiation depend on whether it is alpha, beta, or gamma, and if the radioactive material is inside or outside the body. Alpha is the least penetrating, but is the most hazardous if it does get into the body. In contrast, beta and gamma are more penetrating, but do not cause as much damage within the body. Depleted uranium emits primarily alpha particles, which means that there is no immediate external hazard because alpha particles do not penetrate heavy clothing. Identifying vehicles hit by depleted uranium kinetic energy penetrators is simple. The entry hole will be small and round. In some cases, you may see fin lines surrounding the hole if the metal was soft or thin, such as the aluminum sheet around the outside of the Abrams turret ammo compartment. While all kinetic energy penetrators leave small round holes, only a depleted uranium impact will leave a detectable radioactive signature. In most cases, there will also be spalling around the edges of the hole. The spalling looks like melted and rehardened solder. There will also be radioactive depleted uranium dust on the vehicle surfaces. The depleted uranium penetrator usually goes through the vehicle without breaking up. This results in a small, round radioactive exit hole, only slightly larger in diameter than the entry hole. You may see spalling around the hole or within the vehicle, and burning will usually have occurred. In contrast, conventional high-explosive munitions leave large entrance and larger blown-out exit holes with no radioactive signature. Two other types of radioactive hazards you may encounter on the battlefield are 1. Tritium, and 2. Radium. Tritium and radium are used in self-luminous dials and gauges. Radium in old ones, tritium in new ones. Tritium is not a hazard as long as the dials and gauges remain sealed. If a tritium device is broken on the battlefield, stay away from it and immediately notify your unit chemical officer or NCO. Tritium emits beta particles, but the energy is so low that normal radiac meters cannot detect them. Nevertheless, it is there. Stay away from it. The second type, radium, is a gamma emitter and can be detected with radiac meters. Do not pick up, handle, or take foreign items with dials or devices that glow in the dark. They probably contain radium. Avoid all cracked or damaged dials and gauges. If you suspect contamination, you should use hazard avoidance techniques to protect yourself and your equipment. The three principles of radioactive hazard avoidance are: 1. Time. Minimize your exposure time to the radioactivity. For example, set an operational exposure limit. Rotate your crews to reduce total dose. Or rehearse your mission to improve performance and eliminate unnecessary tasks. 2. Distance. Maximize the distance between yourself and the radioactive source as much as possible. 3. Shielding. Shielding is placing a barrier between you and the radioactive source. Use anything available. In this case, even cardboard, tape, and paint are effective. Your objective is to complete the mission safely and avoid the spread of contamination, specifically the depleted uranium dust. Remember, always keep away from contaminated equipment or terrain if possible. But if you must work with contaminated equipment, follow these specific steps to keep hazards as low as possible. 1. Contact your unit chemical officer and medical officer. 2. Cover up exposed skin by rolling down your sleeves and blousing your pants, or by putting on your mop suit. This reduces exposure because alpha particles cannot pass through the material. 3. Don respiratory protection. If you plan on being in the vehicle or working on the equipment for only a few minutes, a handkerchief or dust mask worn over the mouth and nose will provide adequate respiratory protection. For longer exposures, put on your protective mask. 4. Perform a visual inspection to identify explosive hazards. Destroyed or contaminated vehicles which may contain unexploded or unstable munitions should be marked, secured, reported, and left for specially trained recovery retrograde teams. Caution: if you are in an Abrams, Bradley, or other vehicle that is hit with depleted uranium munitions, you may have unexploded or unstable munitions. These munitions may or may not retain their normal shape. Because depleted uranium contamination is not a hazard requiring immediate decontamination, your commander will decide when to complete operational decontamination if you find radioactive depleted uranium contamination on yourself or a vehicle. To perform operational decontamination, select a site away from water sources, food storage or eating areas, and occupied bivouac sites. Then, brush, scrape, or wash off loose radioactive dust from yourself and/or the vehicle. Mark the area so others know it is contaminated. Depleted uranium that is fixed or embedded on the vehicle may be covered with duct tape, cardboard, or whatever you have available. The location and type of depleted uranium contamination must be reported up command channels through the nuclear, biological, and chemical warning and reporting system. Report the dose and location with an NBC-4 report. Remember, depleted uranium is not an immediate health concern. Treat injuries in accordance with the Soldier's Manual of Common Tasks, STP 21-1 SMCT. If you or your soldiers are injured in a depleted uranium-contaminated situation, follow these steps. 1. Use a radiac meter to check each wound for radiological contamination. 2. Wash out all minor cuts on hands, arms, or legs to remove any radioactive or heavy metal contamination. 3. Contact the medics. For all major wounds, leave embedded particles in place and tell the medic that radioactive and heavy metal materials are involved so that appropriate medical care can be provided. 4. Mark the field medical card, DD Form 1380, to indicate radioactive and heavy metal contamination. Awareness of depleted uranium hazards and common sense procedures will effectively protect you until the contamination can be removed or your equipment can be replaced. Remember, depleted uranium is not an immediate hazard. The two health concerns about depleted uranium are heavy metal toxicity and radioactivity. If you are involved in a depleted uranium situation, 1. Minimize your exposure time. 2. Maximize your distance from the depleted uranium. And 3. Use protective clothing and any shielding available. Bottom line, unless you're involved in a detonation or fire with depleted uranium, hazards are relatively small. Operation of the ANPDR-77 Radiac set. Radiological contamination is a potential hazard, whether on the battlefield or off. It can be a threat to unprotected personnel and the mission. It is imperative that contamination be quickly identified to minimize that threat. Older radiation detection equipment, such as the ANPDR-27, ANPDR-56, and the Fiddler probe, are not as accurate or responsive as the newer generation. Employment of the new ANPDR-77 Radiac set improves the efficiency and range of detection and measurement operations, whether on the battlefield, in nuclear accident and incident response and assistance, or in routine monitoring for health and safety. The ANPDR-77 Radiac set incorporates the beta-gamma detection capabilities of the ANPDR-27, the alpha detection capability of the ANPDR-56, and the X-ray detection capability of the Fiddler probe. This one set of portable radiation detection equipment can be configured to measure beta-gamma, alpha, and X-ray contamination. The set also includes accessories and basic test and repair parts for maintenance. The set weighs approximately 27 pounds. The Radiac meter is battery powered. It has a cable plug to connect the various probes and an enclosed speaker for audio alarm and chirps. Rates are shown on the display screen. Trend lights indicate an increase or decrease in rates. Trend lights also act as visual alarm lights when flashing. The control panel has switches and buttons which are used during operation. Let's look at the different probes, beginning with the beta-gamma probe. It is stored in the pouch. A receptacle for the Radiac meter cable is located on the end opposite the detector. A probe window cover protects the detector from damage. The probe window cover is left closed when used to detect and measure gamma radiation, but must be opened when used to detect beta radiation. The operational ranges of the Radiac meter with the beta-gamma probe are: background to 999,000 millirads per hour. Low-range detection of beta radiation is 1 microrad per hour to 5 rads per hour. Next, the alpha probe. The receptacle for connection to the meter on the alpha probe is located on the end. The bottom hinged cover is secured by a thumb screw. The delicate mylar window is protected by a cover, which is stored in the pouch when not in use. The window is further protected by a grill in the hinged cover. The alpha probe is secured to the outside of the pouch for carrying. The operational ranges of the Radiac meter using the alpha probe are: background to 999,000 counts per minute, background to 180 microcuries per square meter, and background to 999,000 disintegrations per minute per 100 square centimeters. Third and last is the X-ray probe. The X-ray probe has its own batteries, low battery indicator, an energy select switch, a connecting receptacle, and a peak align adjust, which is used only in extreme cold. The handle is adjustable to place the probe at the correct height, which is 12 inches above the surface being monitored. The probe's window is fully exposed and unprotected. Caution: the X-ray probe's window is easily damaged. Never set it on a surface that could press on the window or allow it to strike objects. With the X-ray probe, the operational ranges are background to 999,000 counts per minute. The Radiac set contains spare mylar windows, a pen light, lacquer, a screwdriver, and a black photo cloth for maintenance, a radioactive test sample, a strap for carrying the pouch, a waterproof technical bulletin, and a technical manual. It also contains a headset with volume control for improved audio during operation. Before each mission, pre-operational tests must be performed on the ANPDR-77. The operator initiates the tests, operates controls, and observes for proper displays. The Radiac meter is self-testing, and pre-operational tests are performed automatically by the equipment once initiated. The tests can be performed with any of the probes connected to the Radiac meter. Each time a different probe is connected, the Radiac meter automatically adjusts its operating characteristics. The change is indicated by the displayed arrows. There are 3 arrows. Only the top 2 arrows are displayed with the beta-gamma probe. For the alpha probe, the operator can change selection to any one of the 3 display arrows. For the X-ray probe, the connection will display only one of the 2 top arrows, either of which can be selected by the operator. Note, an incorrect arrow display indicates the Radiac meter is malfunctioning and should be turned in for maintenance. There are 4 pre-operational tests. 1, segment. 2, alarm. 3, digit unit. And 4, electrical, which are done in sequence. The first test displays segments of the digital display, decimal points, and unit readouts for about 10 seconds. This will show that all display segments are working. To initiate the segment test, set the power switch to on. Wait for the arrow display. Set alarm switch to chirp. Press and hold the clear test button until the alarm sounds. Release the clear test button and the display will appear. The display must read 0.8, 0.8, 0.8 K with 3 arrows. The alarm test must be performed during the 10 seconds that the segments are displayed. Setting the alarm switch to all positions ensures that the alarm sounds and shuts off, and that the lights work at the proper time. During the 10 seconds the segment display appears, set the alarm switch to Viz. The alarm stops. Set the alarm switch to alarm. The trend lights come on. Set it to chirp. The lights go out and the alarm sounds. Returning the alarm switch to Viz silences the alarm and ends the alarm test. The digit unit test begins with 3 zeros and sequences through numbers, decimal places, and dose units to test that they are all working in proper order. The electrical tests begin immediately after the 999K display. The 1-digit codes which are shown do not pertain to the pre-operational test and can be ignored. The flashing 9 with the pulsating alarm indicates all tests are a go. A flashing 0 at the end of the pre-test or during operation indicates a problem. Note, any time a flashing 0 is observed, turn off the Radiac meter and report it to your supervisor. The last step is to operate the clear test button, and the display will cycle through 3 zeros. 3 zeros with arrows, then a background dose rate. The Radiac set is ready. It will continue to automatically test itself during operation. Depending upon your mission, you may choose to activate some or all of the available features. This includes the chirp and alarm settings, alarm set point, background subtract, filter selection, update time, and scaler feature. The most commonly used features are the chirp alarm, alarm set point, background subtract, and filter selection. Survey and monitoring operations can be performed by listening for chirps and tones, by visually observing the meter, or using both visual and audio means. Chirp selection is made using the 3-position alarm toggle. At higher rates, the chirp becomes a tone. Chirps and tone are also heard in the headset. Placing the switch in the visual position will silence the chirp or tone. In this position, the audio alarm is disabled. The alarm lights. Trend lights and count rates must be visually observed by the operator. Both the alarm lights and the audio alarm will continue to function when the switch is in the audio-visual position. The rate at which the alarm will activate is set into the Radiac meter using the TM or TB. The background subtract is an operating characteristic of the ANPDR-77 that obtains a background reading, which it will then subtract from all subsequent foreground readings. The internal filter smooths out some of the random variations in a reading. The filter feature is either selected or not selected, depending on your mission. When you prepare the meter for a beta-gamma survey, select and set desired features. This includes setting selection of filter, update time, chirp, alarm, and alarm set points. Always do a background count. No further checks are required. The probe can be carried in the pouch or held in the hand during survey operations. For gamma detection, the window cover on the end of the probe must be closed. It is open during beta detection operations, and the audible alarm should be used to allow the operator to watch the positioning of the probe rather than watching the meter display. When you prepare the meter for alpha monitoring or survey, turn the power on and observe the background reading. Position the arrow to the choice of units desired for the alpha monitoring operation. Select and set the operating features for the alpha probe. With power on and features set, remove the access cover. Centrally locate the test sample between the probe mounting feet with the alpha side facing the Mylar window. The display should read between 7,000 and 14,000 counts per minute. Remove and replace the test sample in the case. Monitoring is normally performed with the alpha probe within 1/8 inch or directly on the surface being monitored. Sweep the surface in a stop-go fashion, allowing time for detection, reaction, and display. To prepare for an X-ray mission, check the X-ray probe operation. Set the meter to filtered mode and 2-second update. Set the probe to peak align and place the test sample under the probe, X-ray side facing up. The meter should display 8,000 to 16,000 counts per minute above the average background counts. Remove the test sample and reset the probe energy to the desired kilo electron volts. Set the meter to the unfiltered mode. This allows recording of the background count. X-ray surveying and monitoring is performed with the extension handle positioned to maintain the probe at 12 inches or less above the surface. Other than routine preventive maintenance checks and services to the Radiac set's components, accessories, and case, the only specific operator and unit maintenance authorized are repair and replacement of the Mylar window and replacement of the batteries. Flashing arrows on the display indicate a low battery condition. It tells the operator that about 5 hours of useful battery life remains and that they should be changed at the first opportunity. An increase in display readings when the cover is removed from the alpha probe indicates a damaged Mylar window. The alpha probe's Mylar window can be replaced, or in the case of a pinhole, repaired. To locate pinholes with the cover on, turn the alpha probe to face a light source. Observe the meter or listen on the headset and slowly remove the cover. Stop removal when the meter or headset indicate an increase in count rate. Now, completely cover the probe face with a light shield. Slowly remove the shield at a 90-degree angle to the probe cover. Stop when the meter or headset indicates an increase in count rate. The intersection of the access cover and light shield indicates the vicinity of the leak. Note grill opening location. Caution: to avoid damage, always perform the following procedures in a darkened area or beneath the photo cloth light shield. To verify the location, cover the probe with the photo cloth and point the pin light at the suspected grill opening. An increase in the reading indicates the location of the leak. Remove both access cover and light shield. Mark the isolated leak with a very small dot of lacquer through the grill opening. Loosen the captive screw and turn the probe face up and open the hinged cover. Exposing only the hinged cover, the Mylar window is ready for repair. To repair a pinhole, increase the size of the lacquer dot to about 1/4 inch. Allow the repaired Mylar windows to dry a minimum of 10 minutes. If the Mylar window is not repairable, replace it with a spare from the carrying case. Install the new Mylar window into the hinged cover and onto the locating pins with the frame side facing down on the grill. Close the cover on the photo cloth. Carefully slide the cloth out and tighten the captive screw. This completes repair or replacement of the Mylar window. The probe is now ready for use. Minimizing the hazard of radiological contamination on personnel and equipment is essential to mission accomplishment. Employment of the ANPDR-77 Radiac set enhances radiological survey and monitoring operations. With its multiple functions and portability, it provides increased efficiency and capability in detecting and measuring radiological contamination.
Load it. Check my rear. Make sure you don't sneak up behind me. Come on. Go. Oh, no! Ah! Yeah. Everybody okay?
BDAR is any action taken to rapidly return equipment to the operational commander. This is accomplished by expediently repairing, bypassing, jury-rigging, or cannibalizing components to restore minimum functional combat capability or to allow self-recovery. Repairs are temporary and may not restore full performance capability. BDAR was previously restricted to wartime conditions, but training is necessary during peacetime. The first priority is to take care of any casualties. The following safety checks must be made to prevent any more casualties. Is there a round of ammunition in the tube? Is any ammunition in a dangerous state due to fire or physical damage? Has fuel, oil, or any combustibles accumulated? Is the wiring safe? Is the fire extinguisher system operational? Stand by with a portable fire extinguisher, or be prepared to manually operate any onboard fire extinguishers. If possible, the crew will make an initial assessment on how long it will take to get back into action. This must be reported to the next higher commander, who will make his decision based on MET-T. The initial after-action report should include the following: the location of the vehicle, firepower status, mobility status, communication status, current and anticipated enemy action, and a casualty status. In the meantime, the crew should make any crew operator repairs they can. If possible, the vehicle should be moved out of enemy range or observation while making any repairs. The BDAR team will be from the Forward Support Maintenance Company. Whether it is mechanized infantry or tank system support, the personnel will be the same key MOSs. A unit mechanic for the specific equipment, in this case 63 Echo, 45 Golf fire control instrument repair, 45 Kilo tank turret repair, 63 Hotel track vehicle repair, 63 Whiskey wheel vehicle repair, and 29 Echo radio repair. When the maintenance team arrives, the team chief will consult with a senior crewman and then perform a thorough assessment. This will consist of reviewing the crew after-action report, interviewing the crew, visually inspecting the damage, and performing a self-test and diagnostics test with proper test equipment if possible. This information will tell the maintenance team what must be repaired or replaced, the sequence and priority of repair, and the total repair time. The goal is to fix forward at the down site in the least amount of time. Although standard maintenance should be applied at the UMCP, BDAR may be applied if parts and equipment are not available. To be effective, BDAR should be accurate and flexible. Make sure that man-hours, parts, resources, and time are not wasted. Maintenance crews should be cross-trained so that the absence of key personnel will not jeopardize the mission. The BDAR team will do the assessment first. Do not attempt to operate systems or subsystems until one is completed. The basic rules of assessment are: trace each round or piece of shrapnel from entry to exit. Look for secondary damage. Look for and trace the path of ricochets and spall splashback. When necessary, seek support from other units. BDAR is a team effort. Crew, organizational, and DS mechanics must work together and pool resources to accomplish the mission. Since maintenance teams lack heavy weapons and communications, they must rely on the supported unit for these resources. Hidden damage is caused when shrapnel ricochets inside vehicles and becomes embedded into other items. For example, electrical cables and hydraulic hoses may be damaged. The following vehicle components and subcomponents are vulnerable to enemy fire or normal failure. They are the suspension or wheels, electrical systems, cooling systems, fuel systems, and hydraulic and oil systems. Enemy action, accidents, and normal maintenance failures are not restricted to these areas alone, but they are the most vulnerable. Warning: if the vehicle is depleted uranium or NBC contaminated, it must be designated with NBC markers. If markers are not available, use paint or any field expedient to mark the vehicle. The vehicle will be recovered to a decontamination site prior to evacuation. Assessment and repair is faster and easier if a systematic approach is taken. This can be accomplished by using the assessment forms found in the BDAR TMs. These forms can be reproduced locally. Use the forms and the TM. Do not rely on your memory. The stress of combat makes one's memory unreliable. In addition, the forms must accompany the vehicle if it is evacuated. As soon as possible, standard maintenance must be applied to the BDAR fix. Each BDAR fix must be tagged by a DD Form 1577. If the tag is not available, any conspicuous tag will do. Marking the temporary fix will quickly aid mechanics in identifying what must be repaired. Line tags is not possible A warning notice will be placed in the operator's compartment or where the vehicle commander is located. Mark the tag BDAR and write down the limitations of the vehicle. If a part is cannibalized, tag the area where the part came from to alert mechanics. Soldiers throughout history, especially since World War II, have used temporary field expedient fixes to keep their equipment going. A great step forward has been the development of several ground equipment BDAR kits. Each is a self-contained, standalone kit that weighs approximately 46 pounds. The components allow expedient repair of oil and fuel lines and hydraulic lines, metal patching and repair, reservoir repair, and electrical repair. Each kit has its own NSN and can be ordered through the supply system. The kits are designed for organizational and direct support mechanics. Components can be replenished through the supply system. The kits are the M1 2510-01-327-4170, the M88 2510-01-327-4172, and the M23 generic 2510-01-327-4171. These BDAR kits share many of the same components, but one of the biggest differences is the size of the hydraulic fittings. With any of the above kits, all vehicles and its equipment can be repaired to some extent. The M23 generic kit will support all other equipment and vehicles. These kits fill the technological gap that previously existed between standard supplies, tools, and BDAR. Of equal importance to the kits are the BDAR TMs. Each major system or series of vehicles has a TM that specifically explains how to repair battle damage for that system. Repair only what is needed. The objective is to get the system back into the battle. Forget cosmetic repair. Battlefields are chaotic. Missions and priorities may change at a moment's notice. Some repairs may not be in the manual. Flexibility and ingenuity in thinking are a virtue. Make no assumptions. Trace each round or piece of shrapnel. False assumptions waste time and effort. Think safety. Be on the lookout for spills, damaged electrical cables, wires, live and loaded ammunition, and damaged weapons. Equipment that has been in enemy territory or unsupervised by friendly forces should be checked for booby traps. If at all possible, have EOD check it out. Recently, FM 20-30, Battlefield Damage Assessment and Repair, was published. In fiscal year 95, FM 9-43-3, Battlefield Recovery and Repair, is scheduled for publication. FM 9-43-3 will be a consolidation of FM 20-22, Battlefield